Dear students, in the last module, we studied about approximate methods in quantum mechanics. We learned that approximate methods are needed in quantum mechanics because the fundamental equation of quantum mechanics, that is the Schrodinger equation, cannot be solved exactly for a chemical system containing more than one electron. Since most of the chemical systems contain more than one electron, therefore, in order to solve them, we need approximate methods. Normally, there are two major approximate methods in quantum mechanics. One is the perturbation theory and second is variation method. In the last module, we also studied about the details of perturbation theory. In this module today, we will study about the applications of perturbation theory. So that is basically going to be the focus of this module. After studying this module, you will be able to write down the Schrodinger equation for a complex system using the perturbation theory. That's very important because that is the first step if you have really to apply perturbation theory. And then once we have understood the whole method, we will solve this Schrodinger equation for two systems. One will be a physical system, that is a particle in a one-dimensional box with a slanted bottom. And second would be a simple chemical system, that is helium atom. Let's recall what we have learned about time-independent perturbation theory in the last module. See, the basic problem is that we need to solve the Schrodinger equation for the system. And the Schrodinger equation for the complex system is H cross psi is equal to E psi. This is the equation which we need to solve, but we cannot solve. Therefore, in perturbation theory, we apply a method which will solve this Schrodinger equation by providing successive corrections to an unperturbed problem. So you can see here that the exact Hamiltonian H cap can be written as sum of these terms H0 cap plus lambda H1 cap plus lambda square H2 cap. These are the various terms in the Hamiltonian equation. Then the corresponding wave function psi is equal to psi 0 plus lambda psi 1 plus lambda square psi 2 and so on. And the correspondingly total energy of the system can be written as E0 plus lambda E1 plus lambda square E2. In these equations, if you see carefully, the first term, that is H0 cap, psi 0 and E0, these are the first terms on the right hand side of the equation. These equations and these terms basically represent the unperturbed system, whereas the rest of the terms in these equations represent the correction terms which include perturbation effects. So this is a very important point which you must keep it in mind. Now you all know, and we have already studied in great details, that the perturbation theory is based on certain assumptions. And these assumptions are that the perturbed Hamiltonian is only slightly different as compared to the unperturbed Hamiltonian. That means H cap, which is the perturbed Hamiltonian, that is the total Hamiltonian of the system, is made up of H0 cap, which is the Hamiltonian for the unperturbed system, plus correction terms. And similarly, eigenstates, that means the wave functions and the eigenvalues E, corresponding to unperturbed Hamiltonian are known. This is also very important. That means E0 and psi 0 values are known. Those are very important, and these are the fundamental assumptions of the perturbation theory. We will apply perturbation theory, as I have already mentioned, to two systems. One will be a model system of a particle in one-dimensional box with slanted bottom, and later on we will apply it to the simplest chemical system of helium atom, and for both of them Schrodinger equation cannot be solved exactly. I will also like to tell you here at this stage that in the equations which I mentioned earlier, we said lambda, then lambda square, etc. So those were the successive corrections which were called the perturbation effects. However, in these applications, we will consider only the first order perturbation effect, and that will be the basis, and therefore the corresponding perturbation theory which we will be using in these applications would be the first order perturbation theory. So in this first order perturbation theory, the total energy, wave function and the Hamiltonian of the perturbed system will be written as H cap is equal to H0 cap plus lambda H1 cap. Similarly, psi will be equal to psi 0 plus lambda psi 1, and E would be E0 plus lambda E1. You can see here that is in these equations we have ignored the second order terms, that means those terms where lambda square was there, that is not being considered. Therefore, only the first order correction to the perturbation theory is taken. And as we have also learned in our last module that once we study first order correction, then on solving this equation we get total energy and the wave function which incorporate these first order corrections, and then the corresponding energy is E is equal to E0 plus integral psi 0 star H1 cap psi 0 d tau, and the corresponding unperturbed wave function is equal to psi 0 plus summation m integral psi m star H1 cap psi 0 d tau divided by absolute value of Em minus E0 psi n not being equal to 0. So these are the basis of the first order perturbation theory. And now let's study the applications of all these to the two problems we mentioned already. Let's first consider the application of this first order perturbation theory to the problem of particle in a one-dimensional box with slanted bottom. So this is one of the simplest cases to understand the perturbation theory. As you have already learned, we first of all have to understand how to start with this. Here we consider a particle in a one-dimensional box. Here you can see that there is a particle of mass m in a one-dimensional box. This box is along x-axis, and you can see here that its bottom is slanted. Outside this box, the potential energy is infinity, but inside this box, as you can see here, potential energy Vx is equal to kx upon L, and the length of the box along x-axis is L. That means it varies from x is equal to 0 to x is equal to L. So this is basically the representation of a particle in a box with a slanted bottom. Now, if we have to solve the Schrodinger equation, we have to first of all find out what will be the unperturbed part of the problem, and then we will apply the successive correction. The unperturbed terms for this box would be the corresponding H0 cap, which is the unperturbed Hamiltonian, that would be minus h square upon 8 pi square m d2 by dx2. Here in the unperturbed part, we are taking potential energy to be 0, and the only energy is the corresponding kinetic energy. And we all know that for this problem, Schrodinger equation can be solved exactly. And if the equation is solved exactly, then the corresponding energy which we get for a particle in a one-dimensional box where potential energy is equal to 0 is n square h square upon 8 ml square. This is the total energy which we get. And the corresponding wave functions for that particle for the unperturbed part are 2 by L under root, L is the length of the box, sine n pi x upon L. N will be 1, 2, 3, n cannot be 0, please remember that. Now equations which we have already studied, we can see that the perturbed Hamiltonian for this particle in one-dimensional box with slanted bottom will be, as we have discussed in the equation, this will be kx by L. H1 cap is equal to kx by L. This is the unperturbed Hamiltonian for the particle. K is a sort of a constant which represents the potential energy. It will be constant for a given system, and since x can vary from 0 to L, therefore H1 cap will vary between 0 to K. Now if we substitute this equation into our earlier equation, we get straightway the first order correction to energy due to perturbation. And as you can see, we are solving this here. We are calculating the first order correction to energy due to perturbation. Psi 0 star, as you know, is, we have already mentioned how the wave function looks for an unperturbed system. Then we put H1 cap, which is the corresponding correction which we just mentioned, and if we substitute all this, we get the corresponding first order correction to energy due to perturbation, which comes to be K by 2. So from this equation, we can see that the first order correction to energy due to perturbation is equal to K by 2. If the bottom were not slanted, then K would have been 0. And in that case, this correction term would have been 0, and that means the whole problem would have been the normal problem of a particle in one-dimensional box. But once there is a slanted bottom, there is a correction to the energy due to perturbation, and this correction is equal to K by 2. And that shows that this first order correction to the perturbed system therefore shifts the energy levels by a factor of K by 2 in comparison to the unperturbed system. So please remember that unperturbed system had the energy equal to n square h square upon 8 ml square. But once the perturbation effects are considered, the corresponding energy becomes now n square h square upon 8 ml square plus K by 2. So this K by 2 is the corresponding correction which we have been able to find out using the first order perturbation theory. So after having considered a simple application of first order perturbation theory to the problem of a particle in a one-dimensional box with slanted bottom, let's now consider the next simplest chemical system, that is a system containing 2 electrons, and that is helium atom. Now we will see how we can apply first order perturbation theory to solve the problem of helium atom. As you all know, and as you can see from here, that helium atom is a 3-particle system, 2 electrons and 1 nucleus, for which the Schrodinger equation cannot be solved exactly. If we look at the corresponding Schrodinger equation for the helium atom, it looks like H cap is equal to minus H square upon 8 pi square ME, where ME is the mass of the electron. Then we have del electron 1 square plus del electron 2 square. These are the corresponding kinetic energy terms of electron 1 and electron 2. Then the next term is minus H square upon 8 pi square Mn del n square. This represents the kinetic energy term of the nucleus. And then we have two terms, minus 2e square upon 4 pi epsilon 0 r1 minus 2e square upon 4 pi epsilon 0 r2. These are the attraction terms. These basically represents the potential energy of attraction between the nucleus and electron 1, and second is the potential energy of attraction between the nucleus and electron 2. And the last term in this equation, electron-electron repulsion term, and that is E square upon 4 pi epsilon 0 r12. Here r12 is the distance between the two electrons, and as you can see also from this equation that this term has a positive sign. Why this term has a positive sign? Because potential energy of repulsion will be adding energy to the system. Therefore, it has a positive sign, whereas the rest of the terms, the first two terms which we said are the potential energy terms of attraction, they are having negative signs. Now this we have studied that this is the total Hamiltonian of the helium atom. Now if we want to solve the Schrodinger equation for the helium atom, one of the first assumptions which we first make is that we consider nucleus to be fixed at the origin. And there is a justification because the mass of the nucleus is much larger than the mass of electron. And once we fix the nucleus to be stationary, then its kinetic energy term vanishes, and therefore Hamiltonian reduces to this form, as you can see here. And if we compare it with our earlier equation, we see that this term minus h square upon 8 pi square mn del n square is no longer present in this, because that was the term which was representing the kinetic energy of the nucleus. At this stage, I would also like to mention that in this equation, the last term which we already have mentioned as the interelectronic repulsion term is the term which causes difficulty in solving the Schrodinger equation. Therefore, if suppose we neglect this interelectronic repulsion term, then the result is that the Hamiltonian becomes a two-body problem, and it has H cap is equal to minus H square upon 8 pi square ME del electron 1 square plus del electron 2 square minus 1 upon 4 pi epsilon 0. In the parentheses we have 2e square upon R1 minus 2e square upon R2, and these two are the attraction terms about which we have already discussed. Therefore, now you can see that if we rearrange this equation, on rearrangement, this equation assumes as you can see, in parentheses, we have minus h square upon 8 pi square me del E1 square minus 2e square upon 4 pi epsilon 0 R1. So these are the two terms in one parenthesis, and in the second parenthesis we have the terms minus h square upon 8 pi square me del E2 square minus 2e square upon 4 pi epsilon 0 R2. So these are the two terms in the second parenthesis. So what does it mean? It basically means that if we consider nucleus to be stationary and at origin, and if we also ignore interelectronic repulsion, then we get helium atom Hamiltonian as a sum of two hydrogen-like Hamiltonians. That hydrogen-like Hamiltonians we call because they are like one electron Hamiltonian, but with a charge of +2 at the nucleus. Or therefore, we can say that the ground state Hamiltonian of helium atom becomes equal to sum of two helium ion terms, one electron Hamiltonian. That's very, very important. And therefore, this zero order ground state wave function for helium atom then can be taken as a product of individual electron wave functions. That means the wave functions of two helium ions not interacting with each other. So that's very, very important, and mathematically it can be represented as psi 0 R1 comma R2 is equal to psi 1 R1 multiplied by psi 2 R2. So where, as we already know, that the one electron hydrogen-like wave functions are given by expressions. Psi is equal to 1 upon under root pi z upon a0 raised to the power 3 by 2 into e to the power minus zr upon a0. We already know that. But in this case, z will be the charge on the nucleus. And in the case of helium ion, this charge will be having the value of 2. Please note that the term A0 in this equation represents Bohr radius. And as a result of this, the ground state helium atom energy, which will be equal to the sum of one electron hydrogen atom like energy, is given by E0 is equal to minus 2 pi square me z square E4 divided by n square h square 4 pi epsilon whole square. Again, the second term would also be the same. So this is like, what does this mean? This basically means that if we consider nucleus to be the origin, and if we neglect interelectronic repulsion energy term, then helium atom would have the energy given by this expression, which is just like the energy of two helium ions. Please remember that in this expression which we just mentioned for E0, Z is the corresponding nuclear charge, and that is equal to 2. Now in this table, you can very easily see a comparison between the energy of the hydrogen atom and the energy of the helium atom and the corresponding energy of the helium ion. On the left hand side, you can see that the energy of hydrogen atom is given by minus 2 pi square me z square e to the power 4 divided by n square h square. In parentheses, we have 4 pi epsilon 0 whole square. Now in this you can very well see Z is equal to 1 and therefore Z square would be also equal to 1. Whereas on the right hand side you can see the expression is the same, and that is coming 2 times because energy of the helium atom is equal to the sum of the energy of 2 helium ions. Expression is the same as I mentioned, but Z here is 2 because it is just like a helium ion, one electron being attracting to a nucleus of charge plus 2, and therefore Z square would be 4. You have also studied atomic units. If instead of writing all these complex expressions, if you want to express this energy in terms of atomic units, the corresponding values are, as you can see, for hydrogen atom, the value is equal to minus Z square upon 2n square, whereas the corresponding energy for the helium atom is minus Z square upon n square. But please remember, Z in the former case is 1 and Z in the later case is 2. So based on this, we can also very easily see that the ground state energy of the helium atom, if we neglect interelectronic repulsion term, is given by 2 times the energy of helium ion, and if we further simplify it in terms of energy of hydrogen atom, we see that the energy of helium atom becomes equal to 8 times the energy of hydrogen atom. This is a very, very important expression. Now the question comes that we have been able to solve the problem by ignoring the interelectronic repulsion term. But then one can say that this is not the exact solution because we are ignoring one very important term. Therefore, at this stage, we will have to apply the perturbation correction, and therefore that interelectronic repulsion term will be taken as the first order correction in the Hamiltonian. That means H1 cap is equal to E square upon 4 pi epsilon 0 R12. This is also important to see here that if we use the corresponding atomic units about which we just mentioned, the corresponding equations which we have already studied will assume the form. And here you can see that the corresponding first order correction to the Hamiltonian will assume a very simple form, and that is 1 upon R12. That is only in atomic units. Now once we have specified the first order correction to the Hamiltonian, now we need to apply the first order perturbation theory to find out the first order correction to the energy. And as we already know and we have studied it, that the first order correction to the energy is given by the expression E1 is equal to integral psi 0 star H1 cap psi 0 d tau. And now if we substitute the corresponding values of psi 0 star, which would be the wave function for the helium atom without interelectronic repulsion term, and if we put all these values, and this equation on integration gives E1 equals 5 by 8 energy of helium ion. This is a very important term, and this represents the first order correction to the energy term which is coming because of perturbation. And now you can very well do it yourself also, that the total energy of helium atom would be E0He, which we have already calculated earlier without interelectronic repulsion term, plus E1, and E1 is the first order correction which we just did, and that was equal to 5 by 8 EHE plus. If we substitute these values, the total expression becomes, as you can see in this equation, the total expression becomes equal to 11 by 2 EH. That is the total energy of the helium atom. So this is a very important application which we have done, and if we substitute here the value of hydrogen atom energy, then the energy of helium atom in atomic units, as you can see here, energy of hydrogen atom in atomic units is half, minus half. Therefore, if we substitute that value here, then the corresponding energy becomes equal to 2.75 AU. This is the energy of helium atom which we have obtained using the first order perturbation theory. If we compare this energy of helium atom, which is 2.75 AU, but with a negative sign, this is very important. Please note that it is always with a negative sign because the system is stable. If we compare this energy with the corresponding experimental value of the energy for helium atom, which is minus 2.9033 AU, you can see that the error is about 5%. This shows what? This shows that perturbation theory gives fairly good results for complex quantum system, and this you have seen in the case of helium atom. We can also have this energy in corresponding electron volts, and there the corresponding values would be minus 74.83 electron volt for the energy of the helium atom using perturbation theory, whereas the corresponding experimental value would be minus 79 eV. We have also shown here that how that integral is solved. You can see here that detailed methodology for solving this integral, which ultimately gives the energy to be equal to 5 by 8 Z. That was the first order correction to the energy is given. Those details are given here. So dear students, in this module, we have discussed today the applications of time-independent perturbation theory in first order to two very important problems. One was the problem of a particle in a one-dimensional box with a slanted bottom, and second was the problem of helium atom. In both these problems, we could reach a solution of the Schrodinger equation by applying the first order perturbation theory. As we have discussed that the perturbation theory is an approximate method that solves Schrodinger equation of a complex system by providing successive corrections to an unperturbed problem. But we considered only the first correction only. That was why it is called first order correction. We have already seen the various equations for the time independent first order correction. H cap is equal to H0 cap plus lambda H1 cap. This is the corresponding equation for Hamiltonian. Then the corresponding equation for energy, which will give the first order correction to the energy, and the total energy would be given by E is equal to E0 plus integral psi 0 star H1 cap psi 0 d tau. So this expression gives the total energy of the system, and the corresponding wave function of the system is given by equation equal to psi 0, where psi 0 is the wave function of the unperturbed system, plus summation psi n star H1 cap psi 0 d tau divided by E0 minus Em absolute value psi n. So we, using all these equations, found out that the first order correction to the energy is given by the expression equal to minus 5/8 energy of helium ion. And ultimately we found that the total energy of the helium atom which we get using this method is about minus 2.75 AU or minus 74.83 electron volt, which is within 5% of the correct experimental value of minus 2.903 AU or minus 79 electron volt. So in the next module, we will study in details about another approximate method, and that is the variation method.